Today, in the first half of the lecture, I'll give you some more background on semi-definite programming. It's not because it would be somehow only relevant to quantum non-locality, but it's because this is one of the things that usually are only mentioned very briefly or not mentioned at all. And then when you try to do some research, you usually need to solve stuff numerically, and semi-definite programming is almost always used there. So I'll maybe tell you at least a little bit and then highlight one of the parts which I find is never really well explained, or I don't know of any good explanations there, and try to explain that one so that you have at least some background or some, let's say, first knowledge about this. So the first half of the lecture is not really related to quantum theory as is, but more to the mathematical methods and numerical methods we use in quantum information. Theory of semi-definite programming. Now, so semi-definite programming, or SDPs, are something that's often used to compute stuff, or even if you have a hypothesis, if you want to prove a theorem, you usually can use SDP to just test it for the simplest cases, whether it is true, or find a counterexample. So it's something that's often used. But it's one of those things that you don't have to understand very deeply to be able to use it and solve it numerically. You just need some kind of good enough understanding, and you don't really have to know how computers solve this. Like, for some of the solvers, like Mosaic, I even have no idea, and they charge 20,000 euros per year if you want to use it in an industry, so it's probably very complicated. But you at least need to know what SDP problems are and roughly how to characterize them, or what you can roughly do with them so that you understand at least what's going on. So we can start with the definition, and we'll define two problems at the same time, and then I'll immediately explain why there's two of them and what does it mean. So here, phi will be Hermicity preserving linear map. And it goes from operators on some Hilbert space to operators on other Hilbert space. The Hermicity preserving just means that if you put in a Hermitian operator, you get out Hermitian operator. Or star on the inside is the same as star on the outside. And then we'll assume that we have two operators which are self-adjoint, so I'll now start writing this SA, but most of the time they'll be just assumed to be self-adjoint. And we should see this as our input variables, or something that we are given as the definition of the problem. And then we have the primal problem, which is to maximize trace of A times X. So A is this one A that we are given. X is a variable over which we maximize. So we can say maximize over X here. And we also get some constraints. And we get a constraint that phi of X is equal to B. So if you put X into this map, you get B. And that X is positive semi-definite. Now, this is something like a linear constraint, because this map, it doesn't have to be isomorphism, it doesn't have to be invertible. So in principle, there can be a lot of operators X such that this map maps them to B. Especially you can imagine this phi of X, for example, can be something like trace of X times B, at which point this just tells you that trace of X is equal to 1. This constraint is the one that tells us that X is a positive semi-definite variable. Okay, this is somehow what makes the problem non-linear and what makes it a little bit more interesting, because it somehow lives in an intersection of the subspace of all of the things that get mapped to B, or a fine subspace, and the positive semi-definite cone. We also have the dual problem. And this one is to minimize over Y the trace of By such that phi star of Y is bigger than A, and Y is a self-adjoint operator on B. Now this is a little bit, so the objective function or the thing that we are maximizing or minimizing looks almost the same. It's trace of the variable with one of the operators. But now the constraints are a little bit different, because instead of assuming that y would be positive semi-definite, we just assume that the image of y is positive semi-definite. By the way, this star, this is the adjoint map. So to define this, if we have a map that goes such as that one, then we can define this phi star on y, and we define this by saying that trace of this against any x is the same as trace of y against phi of x for all x and y. We call this phi star the adjoint map. So what this does is that this defines the action of the phi star as the adjoint map, and it's adjoint in the sense that it's the adjoint of, if you would see this as the Hilbert-Schmidt inner product, then this is the adjoint operator to phi as an operator. So the image of the adjoint map is positive semi-definite, and so it's a slightly different constraint than these ones. Given this, so these are somehow optimization problems that we can try to solve in many different ways, numerically, analytically, and so on. And so some terminology is quite useful, and we say that the one that's often used is that we can have a primal feasible solution, or primal feasible. And this is just x as a self-adjoint operator on A, such that phi x is equal to b, and x is positive semi-definite. So we say that the solution is feasible if it satisfies the such that constraint, okay? So it does not have to maximize this function, it at least satisfies this. It's of course non-trivial that it's not clear whether there exists at least one operator that would satisfy all of the constraints that you can write down. There doesn't have to be, but in principle, we usually want to know that whether there is at least one feasible solution, and if there are more, then we maximize over all of them. And then we get the same thing for the dual. We get the dual feasible solution. Also, I would like to say that this solution is a little bit misleading, because the feasible one is not the actual solution. The feasible one is just the solution to these two constraints. And if you would also have the one that reaches the maximum, that we would call that the optimal solution. Yes, and this is just a self-adjoint operator on B that satisfies the constraints as well. The reason why there's two of these problems is because they satisfy something that we call duality. And what they always satisfy is it's what's referred to as weak duality. And this is just that the supremum over x, which is the primal feasible of trace ax, is always less or equal than infimum over y being dual feasible of trace by. Which just tells you that this value is always less or equal than that value. The proof is rather straightforward, but it's very nice to somehow see it and know how it works, because usually if you write a primal problem, you might be interested in writing a dual problem, and if you want to check that you have written down the correct dual problem to your primal problem, what you can do is that you just check whether the duality holds. So what we now want to show is that this, for a primal feasible, this trace is less than this trace for dual feasible. And we start by showing that this is less than trace over phi star of y of x. Now here we are using two things immediately. We are using the fact that x is positive semi-definite, and that phi star of y is bigger or equal than a. Because if you have two operators such that this one is smaller than this one, and you trace it against something positive semi-definite, the inequality holds as it would hold, between the operators. And you can prove this by just rewriting this by saying that, well, if that's true, then phi star of y minus a is positive semi-definite. But if this is positive semi-definite, then we know that the trace of this against any positive semi-definite operator must be positive, and here, as long as x is positive semi-definite. So this inequality follows from combination of those two things. And it could be rather useful to persuade yourself that this is true and that it always holds. Okay, so in the first step, we just change these two things. In the second step, we are going to move the map to the other side. This is nothing else than just the definition of the adjoint map. Now we can use this constraint because we know x is dual feasible, primal feasible. Get that? Well, and cyclicity of the trace to get the exactly same form. So this is weak duality. Now we can have something that's called strong duality. Which happens if the supremum over x being primal feasible of this trace ax is exactly equal the infimum over y being dual feasible over this trace by. And now the strong duality does not always have to hold because there exist SDPs for which this is not true. The weak duality always holds. We just proved it. The strong duality doesn't have to. If you want to know when this is true, there exists a condition for this called the Slater theorem that you can use and check, and it just tells you that if there exists primal feasible solution with some specific properties, then you have strong duality and this holds. Also, there's the fact that this usually holds. Somehow you can, or it's been proved that this holds for almost all SDPs unless you're trying to define some, unless you are specifically trying to construct SDPs where it doesn't hold. So somehow strong duality is almost always there, and you are in practice very unlikely to encounter a problem which wouldn't have this property. So the good thing about this is that if this is true, what we can do is that we can say like, or we can always, given a primal and dual problem, say that, well, just assume that the strong duality holds and that we have some kind of optimal solutions that maximize this thing and minimize this thing. And then we can just say like, okay, but that means that this is equal to that. And sometimes this gives you enough information to beat some extra properties of the optimal solutions. And this sometimes works. This is sometimes enough to prove some theorems or get some more results. So that's why I'm mentioning this, because the strong duality sometimes can be used to just like plug it in, see what happens. Sometimes it works out. Also, if you're running a numerical solver, it usually tells you something about the duality gap. So it's usually telling you how good your solutions are based on how small the gap between this and that x is. Let's do an example. So we can say that we want to maximize trace of ax such that trace of x is equal to 1 and x is positive semi-definite. Now, what's going on here is that we have to see this as our map. So phi of x is equal to trace of x, which means that dimension of the B Hilbert space is equal to 1. So it's not a Hilbert space, it's just a set of complex numbers, and trace is a complex number, so it belongs to this Hilbert space. Now this, I would somehow, again, try to be careful about this situation. It's so trivial, it can get confusing. No, really, I mean, because the multiplication of the number is the inner product. So, but there's also multiplication of the operators and stuff like that. So we have this kind of thing. Now, what is this? What does this tell us about the operator A? So I wrote it a little bit cryptically because this is x is a positive semi-definite operator such that trace is equal to 1, which just means that x is equal to rho belongs to density matrices on H. So we are trying to maximize the inner product of arbitrary semi-definite operator with x. So let's say you have some kind of energy of a spin system or something like that, and you're trying to maximize this. What would you get? Yes?
The largest eigenvalue?
Exactly. Because you can somehow show that this is a linear function over density matrices, and the maximum of a linear function must happen at the extreme point, which means that, in fact, in this case, you can think of rho as being a pure state, and that trace will just become the highest possible mean value of the observable, which is going to be the highest possible eigenvalue. To formulate the dual, we have to find the adjoint map. Again, this is going to be very trivial because this is a so simple case that it's almost confusing. And so now the inner product between y, so I'll just assume that y belongs to HB, which is now just C, and the inner product between y and phi of x is just the product of y and trace of x, okay? Because the inner product on one-dimensional Hilbert space just multiply the numbers. Well, this should be barred. But okay, if we assume that y is, we can assume it's self-adjoint if we would want to get rid of this bar. And now the way to write this down is to say that this is actually trace of y times identity to x, okay? But now we can say that, but this trace, that's the inner product on the operators on Hilbert space A, okay? So it's something like this expression, but that means that this must be phi star of y. So in this extremely trivial case, we just say that phi star of y is y times identity. So what's the dual problem? You have the primal here, you have the formulas here. What's the dual problem?
The minimum y.
Yes.
Y minus a.
Minimize y such that, what? Yeah. Yes. Do you now see how this also gives the largest eigenvalue of A? Because, as your colleague said, this is the same as saying that this minus A is positive. And if you now assume that, well, A is diagonal in some basis because it's self-adjoint, we can assume that the identity is the same basis. What this would give you is that this would be something like y minus eigenvalue 1, y minus eigenvalue 2, and so on, y minus eigenvalue n. And this must be positive. And you're looking for the smallest y where this would hold. So, which means all of these numbers must be positive. So you just take the biggest one, which is going to be the biggest eigenvalue, and set it equal. Everything else must be positive as well. This is extremely trivial, of course, but it's just a simple example to demonstrate how this works. Now, the interesting thing about SDPs is that you will almost never encounter them in this form. Well, in math textbooks, yes. If you are writing some very specific high-performance code, then some packages, for example, if you are using the Mosaic package for the package for Mosaic in Julia, you have to exactly write down your SDPs in these forms because that's the only form it understands. But usually in practice, we don't do it like that, and you are going to encounter SDPs in many different forms, and you just have to know what is an SDP and what is not. And the key thing to know is that we can have the function that we are maximizing or minimizing, because I can also switch the max and min here, just usually by assuming that there's a minus sign in front of something and pulling it out. The function must be a linear function of your variables, and the constraints must be either equality constraints or positive semidefinite constraints, okay? So, for example, we can have an SDP which is maximized trace of AX, again given x and given phi, such that phi of x is smaller than or equal than b, and x is positive semidefinite. And I claim that this is again as an SDP. To be more explicit about this, to show you how one can transform it into essentially this kind of form, is that we're going to say that, okay, if phi of x is less than b, that just means that b minus phi of x is, let's call it this z, which must be positive semidefinite. So now I just defined what the z means. I introduce it as a new object. And now I say that, okay, but then the conditions are the same as saying that maximizing, so then I can say that, well, this is the same as solving this problem, which is the maximize, still the same function, but now phi of x and z is positive semidefinite. But now we're maximizing over x and z. So I just introduced a new variable, and I hope I did it correctly. And this would be now called the slack variable because it doesn't really play a role in the function you're maximizing. It just somehow includes your constraints. And of course, we can also remove the slack variable by going back at the same road by saying that, well, we can express it like this and then just reduce it to just saying this is positive semidefinite. But now, of course, in order to get exactly the same form, we have to say that, well, now instead of having one variable x and one variable z, so instead of having two variables, we can say that these are something like diagonal blocks of a block diagonal matrix. Instead of having a, we now have to express it as a 0, 0, 0, because then if we call this, say, psi, and if we call this some kind of alpha, then trace psi alpha would be exactly trace xa once you undo the block diagonal product. And of course, we now have to define a new map which would act on the block diagonal structure. So there should be in principle another brackets. And this would give you phi x plus z. So this is a new map that we are defining in terms of the old stuff. And once you do this, this condition just becomes this thing equals to b. Oh, I forgot this constraint when rewriting that thing. This constraint, since we assume psi to be block diagonal, just becomes of this form. And we are maximizing the trace over alpha psi. Yes. Of course, I now never said in this kind of definition that psi would have to be block diagonal. You can think about it, whether you have to specify that or not. Because of course I could specify some constraints with that this is a block diagonal matrix just by putting down equalities that all of these off-diagonal things are 0, but somehow think about it yourself whether that's necessary or not. Because that can also happen, that I can have some kind of constraints that are completely unnecessary. And then if you're solving stuff numerically and you put in unnecessary constraints, you're somehow shooting yourself into the foot because it's going to take longer to solve it. Or maybe the computer will tell you, sorry, you have too many constraints, I'm running out of memory, but maybe you can just reduce them because you don't have to have all of those. This is one of the reasons also why I said in the last lecture that if you would be somehow coding this kind of hierarchy of symmetric extensions, you don't have to code all permutations, you just need to code invariants with somehow swaps of parenting, of neighboring blobs, because first of all, this is easier to do, and second of all, this actually gives you less constraints, so your code will run better. And of course, you can combine this, you can have inequality constraints and equality constraints and more constraints and so on and so forth. And SDPs almost never look like this unless you're in a math textbook. But you can always rewrite, you should be always able to rewrite it in that form, and actually what those packages for numerically solving those are doing is that they are doing mainly that and then calling the expensive, good solvers. Okay. Now I'm going to show you the one thing that it took me like years to figure out properly, and this is either common knowledge among some people or black magic. So now I'm going to show you something looking like black magic, hoping that you'll somehow get closer to the common knowledge understanding of it, because I literally don't know a good explanation of this. What we have here are constraint optimization problems. How does one solve constraint optimization problems? You should have done something like that on mathematical analysis. How do you maximize a function?
Lagrange multipliers?
Yes, exactly. So everybody knows what Lagrange multipliers are and can in principle use them, right? So we'll have a problem when we are given a semi-definite operator and B1, B2 also a semi-definite operators on some other Hilbert space, and we want to maximize trace A of x such that phi1 of x is equal to p1, phi2 of x is less or equal than b2, and x is positive semi-definite. So for what I will be doing, you don't really need to remember how to use Lagrange multipliers, but this is essentially the method by using Lagrange multipliers or of that sort. So now we have a semi-definite problem. We want to find a dual. And what we can do is that we can rewrite it into the canonical form, then find the adjoint map, and then write the dual in that way, and then somehow undo it into more reasonable form again. Or we can do it directly using the following method via Lagrange multipliers. And what we are now going to do is that we are going to look at the type of constraints that we have. So these are the constraints, and we have two types. Was the question or? We have two types. We have equality, inequality constraints. I'm going to be on purpose now a little bit inefficient, but I'll just then tell you how we can do this more efficiently. For every equality constraint, we'll introduce a slack variable. That's just going to be a Hermitian operator. And this should be on B. And for inequality constraint, we're going to introduce a Hermitian variable. That's going to be also positive semi-definite. And now we'll write the Lagrangian, or the problem that we have at hand. And this is the problem that we have is to maximize trace of AX over X in self-adjoint operators on A. But we also have all of these constraints, and we are going to encode those using these slack variables and Lagrangian multipliers. So I'm going to write this down, and I'm going to explain why like this and what is it doing. So here we are going to multiply, or we are going to rewrite this one as saying that, b1 minus phi of x is equal to 0, and we are going to rewrite this one as saying that b2 minus phi1, phi2 of x is positive semi-definite. You multiply this by the y and trace. So trace y b1 minus phi1 of x. Multiply this one by the z1 and trace. And again, multiply this one by z2 and trace. And now, since we maximized here, we go the other way and we minimize over the slack variables. So y being, or y, z1, z2 being self-adjoint operators on B, and z1, z2 being positive semi-definite operators. This notation means that they're both positive semi-definite. And now I claim that the maximum of this minimum is the same as the original problem. Is this immediately clear, or is this like I just wrote black magic? Okay, good. So this is the black magic part. Let us now go through it very carefully. This term is kind of clear. This is just what we want to maximize here. That's obvious how to write. Now, here I never enforce these constraints, but the constraints are going to be enforced implicitly by these three terms. As follows. Assume that we pick some value of x. So assume that I pick some kind of x, okay? Any operator, just random one, as long as it's self-adjoint, and plug it into here. And assume that this is non-zero. So if I choose x such that b1 minus phi1 of x is not equal to 0, then, since this is a non-zero operator, it has well, some kind of eigenvalue or something. But in general, then we have that I can choose y. Then there exists y such that trace over y, and here I put the other thing, is non-zero. Okay? If this is non-zero, it has at least one non-zero eigenvalues. Take the projector onto that, this will become non-zero. Now, by mapping y to something like lambda y, or plus minus lambda, and sending lambda to plus minus infinity, I can make this term arbitrarily big or small. So if I try to maximize over x, and I pick x such that this is not equal to 0, then when I'm minimizing over y, if I can just choose y such that this is not equal to 0, and when I'm minimizing, I can somehow put in these prefactors, because these prefactors I can put in within the minimization over y. And I can put in these prefactors such that now all of these trace will go to minus infinity. I'll make essentially this term minus infinity, and everything will be minus infinity, because something minus infinity plus something is going to be minus infinity. Give or take. So the only way to prevent this thing where this minimum pushes us to minus infinity, so the minimum of the maximum of the Lagrangian, so because we can call all of that thing that we have inside there of L, so this is bigger than minus infinity in principle only if you choose the x in such a way that this is equal to 0. But that's our constraint. That's what we want to enforce. So this minimum over the slack variable just enforces that constraint. Is the black magic now clear? Yes?
But don't you need another maximum then?
No, because I maximum.
But that's inside of the minimum.
Yes. But if I choose this to be 0, then the minimum over y doesn't really play a role. It's like minimum of 3 over x. But 3 does not depend on x, so the minimum is going to be 3. And again, if I choose x such that this is equal to 0, this whole term disappears. This is equal to 0. Y times 0 is 0. Trace of 0 is 0. Does not depend on y. So this term will go away.
So if we choose some x, then we get minus infinity in the minimization. We just throw that x out and try another one.
Yes. You could do that, yes.
Why else does this work?
No. So yes, in principle, we would even in a theory of primals, like in this problem, we can say that the maximum is minus infinity if the set of feasible solutions is empty. So if there is no feasible solution, you say that the maximum is minus infinity, which would somehow make sense from this viewpoint, but that's also like the notation that's then adapted in even without explicitly writing down these Lagrangians and Lagrange multipliers. Okay, you can think about this, but is it at least clear now why and how I wrote this term? Okay, let's go to the next one. Can you see the same idea here? If I choose x, and now we actually have to be careful about signs, because now we can make sign mistakes. So, and we have to make like even number of sign mistakes, ideally 0. So if I choose x such that b2 minus phi2 of x has negative eigenvalue, say, let's call it now mu minus with eigenvector psi minus. So this mu minus is the negative eigenvalue, it's a negative number, this is the corresponding eigenvector, then there exists Z1, which we can just choose to be something like, again, lambda times phi1, such that this trace over Z1, and here we have B2 minus phi2 of x is equal, and now we get this lambda factor here and this mu factor, mu minus. Now Z1 has to be positive semi-definite operator, which means that this lambda here is positive semi-definite, okay? So this number is less than 0. But now, by sending lambda to infinity, we are sending the min of the max of L to minus infinity. So the only way to get rid again of this minus infinity is to choose x such that this is positive semi-definite. But if we choose x such that b2 minus phi2 of x is positive semi-definite, then the trace of this will be always a positive number. Now, what's the smallest thing you can have here as a positive number? Yes, exactly 0. So in this case, since we are minimizing over Z1, you just can take Z1 equals to 0. And you get 0. Yes?
Are you sure about the order of minimizing and maximizing? Because to me it feels like if we would do the minimization for a fixed x, it would work. But this way around, it feels strange.
You mean as in whether this means whether we first go over x or over these things?
Yeah, I think this means we do the maximization over x for fixed y and z, right?
I would actually read it the other way around.
Oh,
like you first have to fix this one and then you have to fix this one. Yeah. Also, let's just assume it doesn't really matter.
Sure.
So there's like theorems when you can exchange limits and mins and max and sups and infs. And we are at a physics lecture, essentially. We are all physicists, so we can assume that whatever we are doing, it's so nice that all of the conditions in those theorems are satisfied and the order of the operations does not really matter that much.
But if we have a fixed y, z, and z, then maximize over x, then we would get plus infinity, right?
Let me get there. I'll explain that in a moment. Okay, so we get, so then if this is positive semi-definite, the obvious choice is to take z1 equals to 0, and then this term doesn't play a role. Now, the same thing happens here, is that x, if x has negative eigenvalue here, I can just choose z2 to be the project multiple of the projector on the negative eigenvalue, have this term go to minus infinity, so you better choose x to be positive semi-definite. Now, I'm already going to like foreshadow that this is not an optimal choice because I already could have said here that you should just maximize over positive semi-definite x and not have this here. I am just somehow, in principle, being inefficient to show you that then you just get some kind of slack variable that you can just throw out of the window. Everything's going to be fine. Now, here's the big trick. What we now want to do is that we want to take the variables for the inner optimization and we want to collect them together. Because it's here, it's here, it's here, and it's here. Which means that now this thing is the same as having the, we have here the min over y, z1, z2, and z1, z2 positive semi-definite, max over x. Okay. Now, the first term is multiplied by a. The second term, this one is trace over y, phi1 of x. Okay, this b1, I'm just somehow putting it away into like a different part of the trace. So like I'm breaking up this trace due to linearity. So I have here y, phi1 of x, but then I can use the adjoint, like I can just replace this phi1 of x by x, and I can move the phi1 acting to y. So I can just put in the adjoint map. The same happens here. Z1. And the same happens here, except for now there's no map, so we can just get plus Z2. That closes that and that. And now we get all of these other things that do not depend on x. So we get trace over y b1 plus z1 b2. Okay. Now, here we saw the y, z1, and z2 as the slack variables that were enforcing our constraints, and x as the variable over which we optimize. Here we want to switch the order in which we do stuff, and we want to see this as the constraint, and this part as the value that we optimize, or the function. So we are going to be minimizing, and we are going to be minimizing trace of y b1 plus trace of z1 b2, such that a very important thing now is not to forget about what we have here. Now we get a minus phi1 star of y minus phi2 star of z1 plus z2 positive semidefinite. What we now did is exactly this logic, but in reverse and on this term. And when you think about it, what type of constraint would this be if I am maximizing over x? It would be exactly this constraint, because if this is negative, then you can push it down to minus infinity. No, actually, no. Sorry, wrong line. It's actually equal to 0, because if this is not equals to 0, then I can, if I'm maximizing over x, I can put the value to plus infinity. Yes, sorry. Now the thing is that z2 does not play a role here, so we can now get rid of it as a slack variable. And we do that by realizing that z2 is always equal to phi1 star on y. And by the way, I'm also going to replace z1 with just z, because we are going to be getting rid of z2, so we don't need z1 to be z1, we can just call it z. Okay, so this is now z2. We know it always has to be equal to this, just to satisfy this constraint. And we know that z2 has to be positive semidefinite according to this constraint, so we can just go here. And this becomes our constraint that has now eliminated z2. So then we get our problem, which is going to be the minimize. Z is positive semidefinite, and A is less than phi1 star y plus phi2 star z. And this is the dual. All of this gymnastics are to just find the dual of something without having to rewrite it into the canonical form and using the textbook definition of the dual. Now this is quite useful, because usually, if you are writing down the problem that you want to research, you don't get the dual for free. You just write down the problem and see that, hey, this is a primal for some kind of SDP. It can be with max, it can be with min, it can have many different constraints. But now I want to know the dual. Why do I want to know the dual? Well, because if I have the dual, I can try to enforce this strong duality, set the max equal to the min and maybe get some constraints out of that. Or maybe I just want to see what the dual is because it will be something I recognize as a different type of problem that's been already solved and I can just somehow cite the result from somewhere. Maybe sometimes this problem is interesting in its own or, you know, has some kind of structure that you can use or things like that. So that's why we need to find the dual, and I think this is, once you get used to it, this is the easiest and best method to do that. And with that, we have finally concluded the part on SDPs, and we can start doing something more interesting, or not more interesting, something different. We can start looking into the EPR argument and Bell nonlocality. What is the meaning of Heisenberg's uncertainty principle?
Says if you try to find a machine that measures two observables approximately, you can't get better than some bound.
Yes, as long as they don't commute. Yes, let's try to formalize that a little bit. So we'll start just by looking at local measurements, because then when we start doing the non-local stuff, it's usually contrasted with this. So we can take the Pauli's sigma x and sigma z. They do not commute, so this commutator is not equal to 0 because it's proportional to Pauli y. And from that, Heisenberg uncertainty principle or the Robertson result and all of those things, we get that in principle we should not be able to measure the value of this and that at the same time with infinite accuracy. So what does it mean to measure the value of this and that? I don't know, how do you measure the value of sigma z for a given spin or photon? So what we usually do is that we somehow take a photon and we say that this is some kind of a polarization, horizontal, vertical, pass it through a polarization filter, so you get only the horizontal ones or the vertical ones, and then you have like a photodetector that clicks whenever it detects a photon, and then you get something. So we're not measuring the value of the Pauli operator. We're measuring the probability that your polarization is horizontal or vertical. So in other words, what we have to do is that instead of measuring these two things, we are actually looking at measuring the PVMs. Now, what does it mean for two PVMs that we cannot measure them at the same time? Or in general, for two POVMs? What does it mean that we can measure them at the same time? How would you measure two things at the same time?
Is it device that as well?
Yes, exactly. So we can come to a new definition, and we can say that, well, given two POVMs, because in principle we are not just interested in PVMs, once you start adding noise or detector efficiencies, they become POVMs, and we say that they are jointly measurable or compatible if there exists another POVM, and we are going to now call it GAB. So it's like a POVM, but it's indexed by two indices, such that if you sum over B, this GAB, then you get MA, and if you sum over A, this GAB, you get NB. So what's now the strategy to, if I tell you that MA and MB and NB are jointly measurable, what's the strategy to measure them jointly?
Measure G and compute the marginals?
Yes, exactly. Because these two equations imply that for any quantum state, you'll have the same things. So what you can see is that if I see a single POVM as giving me some kind of probabilities for every A, then I can see it as a probability vector. So I can say that MA gives me nothing else than data, which is a probability vector like this, and NB gives me nothing else than a probability vector that I am now drawing as a column. Then G gives you something like a probability matrix, because it has two indices, but again, sum of all of the elements have to be equal to 1. and they have to be all positive, such that if I sum all of these things together, I get this one, and if I sum all of these things together, I get that one, and for every other value of A and B. Okay, now, in order to save notation, I usually not be using MA and NB, but I'll replace, so instead of MA and MB, I'll replace this by saying that I have MA given X. And now this is a more compact notation because this A is the outcome. So this is the A or B, and this X is which P of EM. Okay, so this just means that MA of 1 is what we had previously, so let's call them tilde now. And this MA of 2 is this thing. Now, assuming they have the same number of outcomes, but if your P of EMs don't have the same number of outcomes, just add outcomes that are always 0 and you'll get this kind of formula. I'm going to be using this format of writing stuff down just because it uses less, it's more compact, and I don't have to write things like this and that, but I just write for every X and things like that. Is this step understandable, clear, and do you know what I'm doing here? Okay, so this is many P of EMs, don't forget that. But this is not the joint P of EMs, this is just notation for many P of EMs. Then we can have a simple theorem saying that these MAX, now this is a many P of EM, so I can just say that these are jointly measurable or compatible if and only if there exists a P of EM G lambda such that where this PA given X lambda are positive numbers and sum over A of PA given X lambda is exactly equal to 1. So what's happening here is that these are many P of EMs, 2 or more, so I can talk about their joint measurability or compatibility, the same thing. And I now say that this is the same as if there exists one P of EM indexed by some kind of whatever index lambda that can run over less numbers or more numbers, or I don't know how many possible values, such that I can obtain these P of EMs in this kind of way. This P of A given X lambda, these are numbers, right? Okay? So these are just real numbers. And we usually call this post-processing because this is a conditional probability. This is the probability of observing outcome A given X, given values of X and lambda, okay? The value of X is given by saying which P of EM am I looking at. The value of lambda is given by this outcome lambda here. So this is just a different way to write down compatibility or joint measurability. Now, of course, we have two definitions. We have to prove their equivalence. And for simplicity, I'm just going to assume that there's just two P of EMs. So X belongs to some kind of set 1 and 2, but you can extend this to as finitely many P of EMs as you want, just the notation is going to be a bit more complicated. And in this case, I can define this 2 outcome or this P of EM just by taking P of A given 1 lambda and P of B given 2 lambda G lambda, and sum over lambda. And if I now sum over A, this one, then this disappears because it's a conditional probability, sums up to 1. I just get the sum over lambda of this, and that gives me exactly the second of the two P of EMs. Now to go the other way. So this proves that if you have this form of compatibility, then we can get into that form. To go the other way, we just observe that if MA is equal to sum over B, GAB, then you can always write this as sum over A prime and B, delta A, A prime, G, A prime, B. And now this A prime B becomes lambda, so I'm now treating this as a multi-index, which means that somehow I compress the two indices into one object. And this P of A, is that given? 1 A prime B, now this is the lambda, is just equal to this delta. And you can verify that this has the requested properties. So what does Heisenberg's measurement uncertainty principle tell us about measurement compatibility? It tells us that we should expect to find sets of P of EMs or P of EMs or pairs of P of EMs, MA and B, that are not jointly measurable or not compatible, because if all of them would be jointly measurable, we could measure everything with arbitrary precision at the same time. So some incompatibility should exist in quantum theory, and that should be responsible for this. And somehow it should be related to this non-commutativity. So we can now do a simple example where we show that these two projection valued measures corresponding to sigma x and sigma z are incompatible. So they're not jointly measurable. This is a known and very, I would say, dated result for PVMs, because actually we know that one of your measurements is a PVM and the other one is P of EM, then they are jointly measurable if and only if they commute with each other. But for pure P of EMs, the commutativity is not necessary and so on. So be careful about concluding stuff from commutativity. It only holds for projective measurements. Nevertheless, this is a very simple and quite known example. And we can prove this by contradiction. Assume that they are compatible. So assume there is some GAB, which would be the joint measurement. Then we must have that 0, 0 is equal to G00 plus G01, and plus plus is equal to G00 plus G10. All I did is that I have explicitly written down these conditions for A equals to 1 and B equals to 1. From this we get that 0, 0 minus G00 is equal to G01, which is positive semidefinite operator. And the same thing we get here. Of course, this thing and this thing can be different, but this thing and this thing is the same. Now we can again forget about the G01 and G10. We just get that this is positive semidefinite and this is positive semidefinite. Now, let us first look at this thing. So we have this. In principle, this is 2 by 2 matrix, and this is a matrix of known form. So this is something like 1, 0, 0 minus, let's call it something like, now I already used those, x, y, y prime z. What can we from this conclude about the x, y, and z? So we get 1 minus x minus y bar minus z. So if you have a matrix, arbitrary matrix, and it's positive semidefinite, then all of the diagonal elements must be positive semidefinite. Because in this case you get that 1 minus x is nothing else than 0, and here we get 0, 0 minus G00, 0, okay? And this minus z is the same but with ones. And since it's a positive semidefinite matrix, this must be positive semidefinite. Of course, this is not enough, but it's necessary. So we get that 1 minus x is bigger than 0, minus z is bigger than 0, but also G00 must be positive semidefinite. So from G00 positive semidefinite, that implies that z is bigger than 0 itself. Aha! But that can only happen if your z is equal to 0. Oh yeah, and here we can also conclude that x belongs to 0 and 1. but that's not really that important at the moment. What can we conclude now about G00? We know that one of the diagonal entries is 0, and the matrix has to be positive semidefinite. What does it mean? If you have a positive semidefinite matrix and the diagonal entry is 0, everything in the same row and in the same column, well, in the same column and in the same row must be equal to 0. Otherwise, it would not be positive semidefinite. In this case, you can prove it by using the determinant trick, that now the determinant of this is x times 0 minus product of these two, so they must be equal to 0. But you can prove this in general. So we get y is equal to 0. Well, yeah, but from all of this, we get that this guy is just some x times this projector, because what we are getting is that there's just this one non-zero entry. Okay? That all follows from this condition. Now, would you believe me if I told you that from this condition you get the same thing, but you get some kind of different x, so x tilde, and you get the plus projector here. It's essentially the same calculation, you just now have to express it in a different basis, and in the plus minus basis, because you can still write down the matrix in arbitrary basis, and you get the same thing. Now, we get that this must be equal to proportional of this project, to proportional to this projector and to this projector, which are different projectors. And this must be equal to itself. What do we get from there?
A contradiction?
No, not yet.
Not yet?
But okay, we can do like a small step before the contradiction to be more explicit.
And we set those equal, and then divide by x.
We get that those two, yes, must be equal to 0. Because what I can do is that I can now sandwich with the minus vector, so I get minus, plus, plus, minus, that gives me 0, and I get minus, 0, 0, minus, which gives me 1/2, from which I get that x half is equal to 0. Sandwiching with 1, here you get 0, and here you get 1 plus, plus 1, and from that you get 1/2. This is also equal to 0. Okay, so, which means that this operator is equal to 0. Now, the only thing specific about this operator is that we somehow started writing stuff from that one, but now I claim that if instead of using 0 and plus, I would use 0 and minus, I would then prove that this operator is equal to 0. If I would use 1 and plus, I would prove that this one is equal to 0. And if I would use 1 and minus, I would prove that the fourth one is equal to 0. And is now the contradiction clear? Because from that we get that 0, 0 is equal to 1, 0 is equal to 0, 1 is equal to 1, 1 is equal to 0. But that's not a P of EM. Actually, that does not even satisfy these constraints. So that's the contradiction. Very well, incompatible measurements exist in quantum theory. And somehow the interpretation here is that you have to make a choice. You cannot measure in the computational and in the Hadamard basis at the same time. If you measure in this basis, you destroy the information that you would obtain from the other measurement. And if you measure the second measurement, you cannot never know what would have happened had I measured in the previous basis. I think also these things work like a training in using the conditionals in English, because it's like what who would have had happened had I measured in the other basis is maybe the correct one. Now what we will start doing is that we will now measure a bipartite state. So far we had just one party measuring their state, and we came to a conclusion that quantum theory has this property that you cannot know everything, you just have to choose what you want to know. Now we are going to start measuring a bipartite state. So we have a state rho AB shared between Alice and Bob, and Alice measures a P of EM MA. What happens after the measurement or during the measurement, or what is the description of the state of the system after the measurement? the Bob?
Take
Or?
the partial trace of our system, the measurement.
Yeah, exactly. So after measuring, we get some object like this, sigma A, which is trace over A. Here you put the state, and here we put the P of EM, and here we put identity on Bob. And this is not the post-measurement state on Bob. This is post-measurement state times the probability of observing this outcome. Okay? So this is not a density matrix. This is subnormalized. And if you sum over all A's, you get something that's a density matrix, because if you sum over all A's, you get something that once you trace it, you get 1. Okay? Or in other words, PA is the probability of observing the outcome A, which is just the trace over that sigma A. Okay. For simplicity, we can assume that Alice measures that they share the Bell state, because this is an easy and nice thing to do. What do we get for sigma A? Or I can maybe write it even this way. Do you remember the one trick that you can do with Bell state that somehow powers all of teleportation and superdense coding? Well, not really superdense coding, but almost. The one trick is that if I have expression of this form, I can take the operator here and put it onto the other system, and the price I pay is transpose. Now there's nothing happening here, so we just put the partial trace over there, and we get MA transposed over dimension of the Hilbert space. This comes from the partial transpose of the Bell state, because from the partial transpose of the Bell state we get identity divided by dimension, and the times identity here can be easily omitted. Now we can look at the easy case where so we'll take dimension to be equal to 2, so just qubits. We have the Bell state, and if we take that Alice measures the sigma z in the sigma z basis, we get that this sigma 0 is 0, 0 divided by 2, sigma 1 is 1, 1 divided by 2. And if Alice measures in the plus basis, we get that sigma plus is plus plus divided by 2, and sigma minus is minus minus divided by 2. I just plugged everything into this formula. Dimension is equal to 2, and the transpose now doesn't play a role because, well, you can assume you're doing the transpose in the computational basis, at which point it doesn't do anything. And these are symmetric operators. So the transpose of themselves are themselves. Actually, on qubits, the transpose only does something to the Pauli Y operator, which sometimes is relevant if you're trying to prove some things, for example, using PPT. Well, yeah. So there's now important if here, because as we know, Alice cannot do both of these things. She cannot measure both this thing and that thing because they are not jointly measurable. They are incompatible. But if Alice measures in the computational basis, then we get this and that. Like this is the outcome. She gets this if she observes the outcome 0, and Bob gets this thing if Alice observes the outcome 1. Okay. But now, if Bob measures in the same basis, he gets the same result as Alice. So, in other words, what I'm saying is that if we have the Bell state here, and we have Alice and Bob measuring in the same, both in the computational basis, you get something like delta ij divided by 2. And for ij big, 0 and 1. So if Alice and Bob measure in the same basis, they always get exactly perfectly correlated outcomes, which means they always both get the same outcomes. But Bob is not Alice. He can be like really far away from Alice. Like in principle, this entangled state is between two particles, and one of the particles can be on Earth and the other one can be like at the end of the other far end of the Milky Way, you know? So there's no way how we can transmit the information about what Alice's outcomes was to Bob and so on. Because this can, in principle, happen so fast that speed of light would play a role. But now if Alice would measure in the Hadamard basis and Bob would measure in the Hadamard basis, again, Bob would get exactly the same outcome as Alice. So Bob would learn the value of sigma x or the Pauli x on Alice's particle. Well, but now we can do an experiment where Alice measures in this basis, in the computational basis, and she gets the value of Pauli z on her particle. But now Bob can measure in the other basis, and he knows that he gets the same outcome as Alice would have gotten had she measured in this basis. In principle, from this it looks like if they measure in a different basis, that then they actually learn the outcomes of both the computational basis measurement and the Hadamard basis measurement, or they learn the values of both Pauli z and Pauli x. So it seems that in this case, if they measure in different bases, they can measure, and if at the end they tell each other what they got, they can measure two incompatible observables on Alice's system. Because Alice measures on her system, and we know that Bob gets the same thing as Alice would have gotten had she measured this in the basis as he measured. Is that a contradiction? Are they now compatible or what? How would you explain this? Is the conditional logic clear? That Bob measures in the Hadamard basis, so in this basis, and gets the same thing as Alice would have gotten if she measured on that thing, which means Alice can now measure in the other basis and get the other missing information. How is that even possible? Or what is a possible way to explain this thing? The particles, they cannot tell each other because they can be light years away in principle. In practice, of course, it would be very nice if we can do this on more than several thousand kilometers, but in theory, they can be like really, really far away.
To explain again how Bob measures what Alice would have gotten.
So if Alice measures in the computational basis, if she observes this outcome, this is post-measurement state on Bob. If she observes that outcome, this is post-measurement state on Bob. If Bob measures in the same basis, he gets the same outcome. Okay, so just this statement. They don't know what they will get, but they know that they'll always get exactly the same thing. But this also holds if I and j belong to the other basis. So you cannot mix these two things. If they measure in different bases, this doesn't hold, but if they both measure in the computational basis, they always get exactly the same thing. If they both measure in Hadamard basis, they again get exactly the same thing. Which means that if we want to get the result of measuring Alice's particle in the computational basis, she doesn't have to do it, Bob can do it. And he learns the thing that Alice would have gotten had she measured. But now Alice can actually measure in the other basis and get the other part of the information. The measurement outcome in this basis.
Does it have something to do with two different particles?
Well, we can do it because it's two different particles, because once you measure a particle, you somehow destroy the quantum state you had there. So if you want to measure two different measurements in this way, you have to have two particles. If you would want to measure in three bases, you can just put here GHZ state and you would have, Alice, Bob, and Charlie, and they would always get, the GHZ state is like this one, but it has not to the second power, but to the nth power there. So then you can get perfect correlations between n parties. Well, okay, if you start adding bases which are not represented by symmetric operators, you somehow have to take into account the transposition here, but let's say we are measuring just in bases where projectors are symmetric operators. The one question here is, can the particles be actually making stuff up as they go, you know? So this is what students seem to be doing sometimes at, if you like have this like oral exams, that if you ask them a question, they start making stuff up as they go. Or I don't know if you do it, I used to do it. Sometimes it works. But now the question is, can the particle, so if you have a quantum particle, we cannot measure two things at the same time, which means that somehow when you measure the particle decides whether it wants to be like that or like that. You know, the photon decides whether it wants to be horizontal up or horizontal down, you know, and if you have also vertical up and down or, well, it decides whether it wants to be horizontal or vertical, it's not up and down. But now it seems that from this experiment that the particles should not be able to make stuff up as they go, because otherwise they wouldn't be able to be perfectly correlated. So somehow the information about what will happen in the measurement should be somewhere in there inside where we're just not accessing it correctly and we're not thinking in the correct terms, okay? This is one of the possible conclusions from this, which means that once you see this, you can, just like the Einstein, Podolsky, and Rosen conclude in their paper, say that it seems that the values of both measurement outcomes of Alice's particles exist and in principle can be obtained using such thinking and such logic, okay? And this can be explained by saying that when this state was created, because in order to create this state, you have to bring the particles at some point very close to each other, because you have to apply some local operations. Like how do you make this state? How do you make the Bell state?
Some crystal, probably.
Parametric dome.
Yeah. Okay, you can do that. At which point you have to have two photons in the same crystal or next to each other, you know, so they have to be very close. Or if you start in computational basis, the usual thing is to put Hadamard and then put C naught. So, but the point is that you have to have some kind of non-local unitary or non-local action that acts at the both particles at the same time in order to create the Bell pair or any other entangled state. That's somehow the definition of entanglement. You cannot get it by local operations and classical communication. Now the question is, during this non-local thing, is it that we are creating a quantum state, or is it that the particles actually come together and agree on all potential outcomes of all possible future measurements, and when we measure them, they just retrieve this information from their database and just sample from it and just tells us like, yeah, with the other particle we already agreed on this and we're going to do this. Of course, I mean, this is a little bit anthropomorphizing the particles, but you can still imagine it like that. And this is one of the possible conclusions that, hey, maybe the particles, maybe this incompatibility is not a feature of quantum theory, maybe it's just a stupidness of our description of quantum theory, and maybe we just need to get better description. So maybe the information actually is in somewhere in there, we just need to somehow crack it open and read all of the possible database, you know, because probably once you measure them, they retrieve the information that they have and then burn the database. So maybe we just need to somehow get all of that. And in the next lecture, we'll look at whether that can be the case or not. Any questions? Does the particle know what the random number is going to get out of the measurement, and are they just like fairly sampled in the universe, or is it actually random number? Or you can somehow say the question like, can I in principle write down a theory where the random number you would get by measuring this state in this basis would be predictable somehow? You know, like this can be a post-quantum theory, this can be a theory to go beyond quantum theory, extends it in any other way. But can we somehow have such a theory? In principle.
Does this lead to the Bell equation?
Yes.
Right? Okay.
Yes, because exactly Bell proves that we cannot have such a theory if you assume that the information in the particles is classical. If you assume it's non-classical, then we already have quantum theory. So we just have to deal with this. I mean, you can either see this as a very deep philosophical result about our world, or you can see this as a thing powering some form of quantum key distribution. I think the second thing is more practical.